наблюдение на звезди и така нататък. Очакваме да направим серия още доста яки неща през останалите седмици от месеца. Но едно от основните неща, които е специално за днешния евент, е нещо друго и то е свързано с Европейската космическа агенция. За първи път от близо 7 години и нещо работиме с истинска организация, която има интерес да комуникира наука. И това е Европейската космическа агенция. Поради някаква причина се навиха да правим с тях събития в продължение на 2 години. Аз лично не разбирам, но им благодаря. Близо 12 събития планираме заедно с тях. Това е първото от тях. Целта ни е да викаме повече интересни лектори, като Зак, които да ни комуникират неща, които те се занимават професионално. Следващото такова ще ни е една от лекциите на голямото ни Рацио, което е на 10 ноември, така че задължително чекнете и това нещо. И стигнахме до лекцията. Днес нашия лектор ще бъде Зак Дикисън. Зак, който се прокашля съджестили близо до сцената, е планетарен геолог или планетолог или нещо от този тип. Не знам как работи на български. Planetary geologist. С негов интерес наистина се запознахме съвсем случайно, тъй като бях в Natural History Museum в Лондон. Обикаляхме там, нали, има динозаври, неща, риби, буркани, много буркани, наредени, нали, в смисъл лудница. И обикаляме там измежду коридорите и намерихме някаква стаичка, където се редяха супер много деца. И обикновено, където има много деца, не ме намират на мен, обаче в случая пише нещо космос. Да видим. Съответно, той имаше тогава една дискусия с... даже тук сме го показали, една дискусия с негов колега, който беше част от презентацията, която сега ще видите. Това за мен беше супер интересно. Опитахме се да я поразвием допълнително темата заедно с него и сега ще видите точно какво сме подготвили. Така че, да приключим с флогореята, нека да представя Зак Дикисън.
Hello, everyone. So we're going to do this in Bulgarian, right? Is that the plan? No, okay, sorry. That's not going to happen. So, you couldn't really choose a more clickbaity sort of title to a talk, could you? I mean, we see a couple of articles a year talking about water on Mars. I mean, even David Bowie sang about life on Mars. And it's a really interesting subject, but there's a lot of things that I think are misunderstood. So we're going to start kind of at the basics of what we're talking about when we're talking about looking for water on Mars, and especially looking for life on Mars. So really it comes down to one thing. There's only one planet, despite any news you may have heard about searching for other life on other planets, there's really only one planet that we know of with life on it. And that's here. You're already here. You found the planet with life. So congratulations. But how do we actually know there's life on Earth? Now, bear with me. I've done a few years of very intensive research on this subject to prove that there is life on Earth. So I've collected some photographs. I hope you'll accept this as evidence that we have found life on Earth. So, first of all, starting with like the simplest thing that we could look for. Is the biochemistry that we see on the Earth. I mean, there's things about the Earth that are really unique just because there's life here. So the color of the atmosphere, for example, when we're looking up at the sky, it's really only that color because there's nitrogen and oxygen in our atmosphere. And the oxygen's only there because there's life on the planet already. So there you go. That's my first proof. There's definitely life on Earth because there's lots of oxygen in the atmosphere that's been created by photosynthetic plants. Next, we can go a little bit more concrete. We see some evidence of microorganisms. So individually, these microorganisms are going to be really small, difficult to see one at a time. But if you look in a small pond or something, you might see a bit of green scum, and that indicates that there's a bit of life there. There's small algae feeding off the sunlight. Now, bigger, I've seen cows as well. There's definitely large macroorganisms on Earth. There's plenty of other macroorganisms. This really covers everything from even small insects to all the way up to whales. So anything like that, anything you can see with your naked eye, macroorganism, it's really big. And believe it or not, there is actually signs of intelligent life on Earth as well. I know, I mean, with the politics these days, it's hard to tell. But this might include anything like the structures we've built or the machines that you can see around you. So, do we all believe now that there's definitely life on Earth? Hopefully? Yeah, maybe. But we're even going to go beyond that and say there's signs that there was life on Earth in the past as well. So using these kind of four main categories, we can actually go through signs that there was life here before. So this one, for example, is it's a picture from the tar seeps in California. And this is a place where hydrocarbons and oil and natural gases actually seep up to the surface, and you can see them just bubbling out of the ground. And we know that oil and gas only is created because there was life in the past, photosynthetic life that was harvesting energy from the sun, and the molecules that they created turned into gas and petroleum, and we can see it bubbling out of the ground. So there's a good example of that. Also, this one might be a bit harder to see, but you can see these small kind of layers in these mounds in this rock. And those were formed by really small microorganisms building up over time, each layer depositing a little bit more on the rim of that rock. And then fossils are probably familiar to you. This one's just an ammonite, a sea creature that lived around the same time as dinosaurs. But again, proof that there was life before. And even though there's not been life on Earth for very long, we can still see signs of buildings and things that were there before. So, broadly speaking, these are the kinds of things that we might look for, you know, if we were looking for life somewhere else. And we can broadly separate it into extant life, and that's life that's still living and exists today, and extinct life, so life that doesn't exist anymore. So keep this in mind. We'll come back to this idea of what types of signs of life we might look for. But the next thing is what does this life actually need to live on Earth? And first thing, there's a whole subject dedicated to exactly what life might need to survive and to even start in the first place. So these are just the real basics, the must-haves. So the Earth has a solid surface and geology, so all the nutrients that life might need. It also has a thick atmosphere to protect it from radiation and to give an environment that life can survive in. And with a thick atmosphere, it means you can actually have liquid water on the surface as well. And the Earth has plenty of liquid water. And from what we know about life on Earth, every bit of life on Earth needs water in some way. And then finally, it needs a source of energy or warmth. And although there's a few forms of life on Earth that get their energy from chemicals or from volcanic vents or geothermal energy, almost entirely, life on Earth depends on light from the sun and energy from the sun. So where else could we actually find all these things? Where else could we find the pieces of the puzzle, another planet somewhere out in our solar system or even somewhere else in the universe that has all these pieces that might support life? So there's loads of places we could look. And just in the past 10 years, we've actually discovered thousands of exoplanets. These are planets orbiting other stars in other solar systems. And just the sheer variety of them is incredible. And it means that we've actually seen planets that are about the same size as Earth. We think maybe they're the same composition as the Earth, and are probably in a distance from their star that water might exist on their surfaces. But I'm not going to talk too much about these because the problem is they're really far away. So if we want to search for life sometime in this century, we've really got to do it here in our own solar system. And that still gives us lots of options. So we have the 8 planets. We've got 4 smaller planets in the inner solar system, 4 gas giants in the outer solar system, and a spattering of moons kind of mixed around. So I think we can all agree that we're not going to look for life on the sun. But let's go through the rest and try to, just by process of elimination, what are the other good places in the solar system that we might actually look for life? So the sun is out. We don't want the sun. Now, the next thing we want is a solid surface. And for this reason, the gas giants are probably not a good place to look. They don't have a solid surface. Their atmospheres are really stormy and turbulent. And so it'd be a really difficult place for life to catch hold. The next thing that we'd like is an atmosphere or an ocean, something that life can actually live in, a medium for it to survive. So if we eliminate all the places that have atmospheres, that takes out Mercury, and it also eliminates a bunch of the moons as well. So this leaves us with a few options, though. So we've got 3 planets on the inner solar system, Venus, Earth, and Mars, and then we've got a few moons in the outer solar system. And there's a huge variety in all of these different bodies. So from the big planets like Venus and Earth, these are all to scale, by the way. They look quite similar in size, but in composition, they're very different. And then you have Mars, which is a bit smaller, and almost the same size as the moons in the outer solar system, other than the tiny, tiny dot that's Enceladus there, just below the Earth. So let's just talk about those moons in the outer solar system first. Now, these are potentially fantastic places to look for life. So places like Enceladus and Europa, they're frozen on the surface, so they don't have an atmosphere, but they're actually underneath their frozen surface. We believe that they have oceans of liquid water that are heated by some geothermal energy coming from within. And Titan is really interesting as well. It actually has bodies of liquid on its surface and a really thick atmosphere. But now we kind of come to the problem with the outer moons in the solar system. Titan does have liquid on its surface, but that liquid isn't water. That liquid is actually methane and other hydrocarbons. So, and that's only possible because it's so cold in the outer solar system. So even if these places might look like they're good places to search for life, the amount of energy that's going to reach them is much, much smaller. It's only 2 or 3% of the solar energy that we get here on Earth. So for that reason, I'm going to bring us in and focus on the planets in the inner solar system. So there's Venus, which has a very thick atmosphere, but unfortunately, because of that really thick atmosphere, the pressure is incredibly high on the surface, and the temperature is really high. So the temperature is actually high enough to melt lead. And when we actually look through the clouds on Venus, the surface is all volcanic rocks. So we can't even really see that there was a history of water flowing across the surface. And Venus looks like a place that, for a very long time at least, has been very inhospitable to life. So not a great place to look for life, and also very hard to visit. Now, Earth, there's plenty of life here. We'll skip by that one. We know that is, as far as we're concerned, the perfect place to find life. And I hope I can probably convince you by the end of this that the next best place that we should look after the Earth is Mars. And there's a few reasons for that. So, first of all, there's actually conditions on Mars at the present day, just under the surface, that might be right for life to exist in a really simple way, even today. But more importantly, we see a lot of signs on the surface of Mars that indicate that in the past it was warmer and wetter and may have actually supported life. So, and that's the third thing is, for Mars, there's a real urgency involved, because Mars is probably the first planet that humans will visit after leaving the Earth. And once humans actually visit it, there's a very good chance that we'll contaminate it with life from Earth. So we do our best to decontaminate the robots that we send. We can't decontaminate astronauts if we send them there. So getting to Mars first and trying to answer this question soon is really important. So we've chosen Mars as our target now. This is where we'd actually like to look for life. But how do we go about actually investigating it? And for a few hundred years, the best way to investigate Mars was to use a telescope based on Earth. So this is a picture of an Italian astronomer named Schiaparelli and the telescope that he used, based in Italy, to observe Mars. And this was the best way at the time to actually conduct research on Mars, was to wait for every 2 years, the planets line up, and there was a window of time, you could get a really good view of Mars with a telescope on Earth. And this is roughly what he would have seen. I mean, it's not bad. This is actually a modern photo. It's taken with an 8-inch telescope, just something common that today a backyard astronomer might have. Any amateur could get their hands on this and take a photo like this. But about 100 years ago, this was like pretty much the best images they could get of Mars. And so we have to think, how much did they know? What kind of guesses could they make about what Mars was like on the surface? And I think the best way to actually make that comparison is to look at this image. So this is the flip side of it. This is, again, it's a picture of a planet and its moon taken with an 8-inch telescope. But this 8-inch telescope is actually in orbit around Mars. And for a change, instead of pointing at the surface of Mars, it turned its camera around and took a picture of the Earth. So when we think about what astronomers were thinking when they looked at early pictures of Mars, it's good to make this comparison, because this is the kind of detail they would have seen. So they made some assumptions. Basically, you can see the white bit at the very bottom on Mars, and they guessed that might be a polar ice cap. And then they went further and guessed that if they were looking at the Earth from afar, the oceans would look really dark. So when they looked at Mars, they thought, well, those dark areas around Mars, maybe those are oceans, and then the light areas are continents. And with this kind of thinking, they produced maps of the planet. So this is based on Schiaparelli's first maps, and you can see that in the green, those are meant to be oceans. And this is about 100 years old, and they've even put the polar ice caps there and continents in between the oceans. So we know that they got some of this stuff right and some of it wrong, but we'll get to that in a minute. So we had to wait a really long time until we knew much more about the surface of Mars. So it took until 1964 when the first Mariner spacecraft by NASA flew by the planet. And this was a really early mission, and it wasn't even able to stop at Mars or go into orbit. It just flew by, took as many pictures as it could as it went by. But before this mission, they thought there was a chance that there might be vegetation on Mars even. But the images that came back, we might think of them blurry by today's standards, but actually it told us an awful lot about the surface. And most importantly, it told us that there was definitely no water, there was definitely no vegetation, and it looked like Mars had been a very dry place for a long time. And we've come a really long way from those sort of images. And now there's actually 2 missions that are operating on the surface of Mars and 6 satellites that orbit Mars currently. And this isn't all the missions that have ever happened. This is currently orbiting around Mars and sending back data every day. And what kind of data do we actually get from this? Well, let's just go on a bit of a journey and just try to look at one spot on Mars and see how far we get. So this is now a beautiful image of Mars, and this is pretty typical of what we can see these days. And this is a really interesting photo because it wasn't taken by a spacecraft that was orbiting Mars and studying Mars. This was actually taken by the Rosetta spacecraft, which was on its way to visit a comet. This is one of ESA's missions a few years ago. And as it passed by, it got this beautiful picture of the whole surface of Mars. And from it, we can kind of compare to the images that the early astronomers would have seen, like Schiaparelli. I mean, first of all, we can say, yeah, definitely on the bottom, it looks like there's a polar ice cap there. Check. They seem to be right about that. But then, when it comes to the dark areas being oceans and the light areas being continents, it starts to fall apart. We can actually see now that the dark areas have craters in them. So they're definitely not oceans. It just seems to be a different coloring on the surface. But there really is a line kind of separating the north half and the south half of the planet. So let's choose an area along that line and actually zoom in on it a little bit. Okay, so now the resolution's improving a little bit. And I don't know if you can see, but there is definitely a clear line running diagonally across the image there. And to the bottom, to the south, there's many more craters, and it's a really rough surface. And to the north, it's very smooth and flat. And there does seem to be a really distinct cliff kind of running between the two. And that's fascinating. To me, as a geologist, I wonder, well, why are those two areas so different? What's going on there? So let's zoom in a little bit closer on this big crater that's in the center. Now we can really see some detail here. So now, looking at this, we can actually see some signs that there might have been water on the surface as well. Down in kind of the bottom left corner of that crater, you can see a little thing that looks like a string going into the crater. And that, as far as we can tell, is a valley that was carved by water. So we have a pretty good idea that at some time there was water inside this crater. But what really interests me is this kind of mountain that we have in the center of the crater. And there's a lot of layered rocks there. I'd really like to have a closer look at that. So let's zoom in again. Wow. Now we can see even more evidence that there was water flowing across the surface. You can see all of these gullies kind of flowing down off the side of this mountain. We can see some darker areas. We see a lot of contrast in the colors. I could go on for days about this in the geology, but I really like, let's just focus on this area here. There seems to be an interesting ridge. So let's have a better look at that. Yeah, now we get a lot more detail. And it's this ridge that I'm really interested in the middle, because it looks like it has a lot of layered rocks, kind of running diagonally across the image there. And to a geologist, layered rocks, if they're sedimentary, are fantastic, because each layer tells us something, a story about what was going on in that environment in the past. So let's just zoom in a bit more. And just for reference, keep an eye on the scale bar on the side here. So just for reference, about the entire surface of Mars is covered with imagery at this scale. And if we zoom in a bit more, we go into the scale of the high-rise camera. And this is a really specialist camera. Only about 5% of the surface of Mars is covered with this resolution, but it's hugely useful. And now I can really see that there's a lot of layering going on in this ridge in the center. So let's go in one step further even. Now we even have some color of the surface. So now, I mean, I'm a geologist. I could spend all day trying to pick apart the layering that I see in the upper left corner here. Could make all sorts of maps and ideas about how this formed and what the different layers mean. But I'm also interested in the other side here. Because, see, these dark areas actually appear to be sand dunes. And that's interesting, because it says something about what's going on the surface of Mars at the moment. So if we zoom in once more, now, I mean, you can even see ripples on the surface of this sand dune. And that's only 50 meters now, that scale bar. So, I mean, almost the size of this room, right? We're really getting an incredible amount of detail here. But something else has caught my eye now. Now that we're really zoomed in, what's this? This really bright object here. This seems weird. Can we actually zoom in a little bit further on this? We can. So, and this is the Curiosity rover, as some of you might have guessed. And this is actually the selfie that it took at that exact location on Mars that we just zoomed in on. And you can even see that little patch of sand dunes, the black in the corner back there. And it's really incredible. I mean, the amount of detail we have about the surface of Mars now. So, even though the rovers are really important, the orbital data that I showed you is really even more important, because the rovers have only covered a few tens of kilometers over the surface, whereas we have the whole planet covered from orbit as well. And you know, just to show off, let's just go one more step in our big zoom in here and see what the rover's actually been up to. And now we can see it's actually drilled a little hole. It's only about a centimeter across, really quite small. And it's actually drilled a hole in to see what the rocks are made of, and it's tested it in its really sophisticated laboratory. And you can even see there's some white veins through this rock. And those are a mineral called gypsum. And gypsum only forms in the presence of water. So we've already come a huge way on our journey into Mars. But this kind of leads us to a question of what is it like on Mars today? So I've already showed you a little bit of evidence that there's water there in the past, but what's it like today? So this is a pretty typical view that you might see on Mars. This is a picture actually taken by a different rover, the Opportunity rover, and it's pretty typical of the surface of Mars. It looks very bleak. It's very dry, it's very dusty, and there doesn't seem to be much on the surface at all to be of interest. But we actually know, because the rovers are there, they can tell us a little bit about what the conditions are like. So we know that in the middle of the day, on the hottest day of the year, it might even get up to 20 degrees Celsius, but only if you're really close to the ground. And then at night, it's going to be minus 150 or more. So not a great place to live. And also the atmosphere is really, really, really thin. So thinner than the highest mountains on Earth. So there would be nothing to breathe. And that atmosphere is made up of CO2 anyways. But we do know that there is an atmosphere because we can see things like the sand dunes that I showed you earlier. And also we can see these dust devils every once in a while moving across the surface. So this is a satellite photo of one, but the rovers have gotten pictures of them as well. So they seem to be a fairly common occurrence on Mars. So we know that it has some atmosphere. If it has wind and it's moving things around like dust devils, it must have some atmosphere. But what about water as well? Well, we definitely know there's water on Mars. So if you ever see a headline saying, water discovered on Mars, be a bit skeptical. We already know there's water on Mars. It's just frozen. So this is an image of the southern polar ice cap on Mars. And the white that you see on the top actually isn't water ice, it's carbon dioxide ice. But underneath that is more than a kilometer worth of water ice. And underneath that ice, there might even be areas that it's melted. And a study last year actually discovered that there possibly could be lakes of liquid water underneath the frozen ice. So now we know Mars has a little bit of an atmosphere now, and it has water there, frozen as ice. So it kind of opens up the question of, well, maybe Mars was warmer and wetter in the past. But how would we actually go about finding that out? Now, this is more where my work comes in. And we use a concept called terrestrial analogs. And this is just basically a fancy way of saying that we're looking for features on Mars that look like more familiar features that we see on Earth. And the thinking is that if we see a feature on Mars that looks like something that we see on Earth, we just accept that it was probably formed by the same processes that formed the feature on Earth. So, just to go through a couple of examples with you. This is on the top, a valley system on Mars, and on the bottom, a valley system on Earth. I chose one in red just to trip you up a little bit, but the craters make it pretty obvious that the top one's Mars. And from everything that we can see about it, it looks very much the same. So this is good evidence to us that both of these features were formed by water flowing across the surface. They have small tributaries that feed into bigger channels down the center, just like a river on Earth. And we see this all across the surface of Mars. And we even see evidence not only that water was flowing across the surface, but that there was enough water to actually collect and pool into lakes and possibly oceans. So here, you can tell which one is Earth. This one is pretty obvious, I'd say. But this is a river on Earth that is flowing down through India to reach the Indian Ocean. And right at the coastline there, as a river meets a coastline, all of the sediment that it's carrying suddenly has to stop. It can't flow downslope anymore. And all of that sediment is deposited, and the river branches out to form a fan-shaped delta. And this is a really common feature that we see all over the Earth, and it's only where a river meets a body of water, either a lake or an ocean. And it's a bit harder to see, the image on Mars, But you can kind of see that the same processes were in effect. You have a valley winding its way across the surface, meeting a possible coastline, and then fanning out into different channels to form a delta. And we can see other evidence that water was standing in oceans and lakes. So on the bottom, this is a picture from the Great Salt Lake in Utah, which used to be a much bigger body of water than it is today. And through time, that body of water shrank. But as the water level went down, waves would cut shorelines into the bank of the lake. And each time that happened, it would create a step. And then more water would dry up, and it would create another step. More water would dry up, and it creates another step. And this process, over and over and over, led to these concentric rings, kind of like rings in a bathtub that's being drained, all leading down towards the center of the past lake. And again, it's more difficult to see on Mars, but we actually see these same features repeated across the surface. And in this image, the Mars image at the top, this actually suggests not only that there was a lake, but there was possibly an ocean in this area. So this is what we do as planetary scientists studying Mars. We take features that are familiar on Earth, compare them to what we see on Mars, and then try to reconstruct the past environments. And what it tells us is there were quite a few rivers flowing across the surface, filling lakes that drained, flowing through more rivers, and eventually possibly into an ocean. And this is kind of the sum of all the work that's been done on this. Just a brief summary. So in green, we have all the places on Mars that have river valleys. The blue little dots are places where lakes have been identified, past lakes, that is. And the blue line there actually indicates the possible shoreline of an ocean that would have covered most of Mars. And so this is where I really wanted to focus my research on. We know a lot about these individual features, but how do they all relate to each other? How is the ocean possibly related to the lakes, to the rivers? How does it all connect? So when I started my PhD 2 years ago, I chose a study area right here, right where all of these features might actually interact together. And to start, I actually just started mapping. Just mapping the common features that I could see. So valleys in green, I put the possible coastline in blue, and I mapped as many deltas as I could. But identifying lakes is a bit more difficult, because lakes are small bodies of water. They don't necessarily leave really obvious shorelines. It's more difficult to identify. But what I did notice is that all the valleys in this area are disconnected. So they only run for a short distance, and then there's a gap, and then they run for a little distance again, and then there's a gap. So my theory was that possibly the gaps between these valleys might indicate where there was a lake in the past, because you would get water flowing down to fill up a lake and then draining out the other side. So to test this, let's just look at one particular gap here. This is the first one I looked at. And on top, that's just a zoomed in top view, like a map view. And on the side, we actually have the topography of the area, so the highs and lows. And immediately, the first thing that you can see is that, yeah, there's actually there's a dip, there's a basin between where these two valleys are. And so then I decided, well, if we can test, how would a lake have actually filled up in this area? Well, we know that if the valley is flowing out to the left-hand side there, that basin would have had to fill up to the line of that in order to flow out in the first place. So I just traced that under the topography and decided that would be the highest level possible for that lake. And then with time, erosion would eventually bring the lake level lower, and you'd get a lower lake as the valley that was draining the lake incised down and got lower and lower. The lake would have to get smaller behind it. And there even appears to be possibly a final lake that was maybe drying up at the very end of the life cycle of this river. And it worked very well. When I looked at the entire area and repeated this process, I can actually see that everywhere that I had indicated that there might be a lake was a perfect gap between the valley systems. So what this indicates is that there was actually not just one or two lakes, but a chain of interconnected 6 lakes, all draining down into possibly an ocean at the end. And we can even, because we have such detailed information of the area, we can even actually start to reconstruct the order that these things happened. So first, lake number 1 would have filled up, and as it filled up, it would have eventually overflowed to start filling lake 2, which would have had to fill up a lot more in order to overflow itself, and that would have actually made lake 1 and 2 into one much bigger lake. And then when lake 2 overflowed, it would have caused a valley, down filling up lake 3, which then overflowed, forming a valley, into lake 4, which then overflowed out to form that big yellow fan, that big delta that you see on the edge, which seems to be at the edge of an ocean. And we can even say a little bit more about this. So lake 4, for example, it looks like the valley that drained it incised so far down, eroded so far down, that the lake itself was completely drained away eventually. So this all just kind of gives us an impression that this was a system that was active for quite a while. Quite a lot of water would have had to go through this system to carve through hundreds of meters of rock. And looking in a bit more detail, we can see individually these lakes have some other interesting features. So remember we talked about shorelines and forming steps as a water body shrinks? You can actually see that these small little steps around this lake as well, indicating that possibly there were other levels of this lake that existed long before this one, and eventually it drained away. And just looking in a bit more detail at the delta at the end here, you can see it's this typical pattern of the valley branching out at the end. And if we look really closely, we can even find out a little bit more that tells us that this was probably a sedimentary fan and a delta. So for one, we can kind of see that the material that the fan is made of is much, much finer, indicating it's probably sedimentary. And also, we can see a lot of fine layering when we look in the craters. And again, all this helps to support the idea that this is something that was active for quite a long time, building up these layers. So this is the study area now, just seen from a bird's eye view. And it gives us an amazing amount of information about this one small area on the planet. That there was possibly an ocean, there were definitely lakes, and there were definitely valleys draining them across the landscape. So the next thing is, well, what if we extrapolate that out to the whole planet? Now, this is just an artist's representation, but it's accurate to the topography. And this is what Mars might have looked like if there was that much water in the past. So it's a huge amount of detail, and it's the perfect kind of place that you might imagine would be great for life. And that's my study area there for reference. So why don't we go? Let's go have a look. That seems like a great place to look. Now, unfortunately, my study area, there's no rovers going there. No plans to send anyone to visit my little lakes. It is sad. But, however, luckily, ESA is sending a rover next summer to this location just to the south. And actually, NASA is sending a rover next year at the same time to a location just quite a ways to the west. But what's interesting is that both of the sites that they're sending their rovers have a lot in common with the site that I'm looking at, in that they're very near a possible shoreline, they're in lakes from the past, and they both have deltas as well. So the hope is that the results of my study will help inform when they get the rovers to these locations and give a broader picture of what these landscapes might have been like. So just to give you a quick idea of what these missions are, this is ESA's rover. So this is the Rosalind Franklin rover. The mission is known as ExoMars, and it's going to launch next summer, land about 6 months later. And its big power, its superpower, if you will, is that it's going to be the first rover to actually be able to drill 2 meters into the surface. Now, the image I showed you before, rovers before have literally only scratched the surface, only like a centimeter deep. So the hope is that by going 2 meters into the surface, they'll be able to find preserved organic material that may tell us whether or not life existed on Mars in the past. But not to be outdone, the much bigger Mars 2020 rover that NASA is sending, it has a much more ambitious goal in some ways. It's going to actually start collecting samples that it's going to cache somewhere on the planet, just to store them somewhere, so that a few years later, another mission can come along, pick up those samples, and actually bring them back to Earth, which would be a huge accomplishment if we can make that work. So we just want to talk, if you remember this, my examples of why there's life on Earth. So when we talk about the rovers looking for life on Mars, which of these types are they actually looking for? Well, you might be disappointed, but we're not looking for the cows. We're not looking for the intelligent life or little green men. Almost entirely, these missions are going to be focused on the biochemistry and possibly looking for microorganisms, whether that's extinct or living currently. And I know this might be a bit disappointing, but there's a really good reason why we're focusing so much on just the biochemistry and the microorganisms. And that's because what we know about the history of life on Earth and the history of Mars. So we know that both planets formed around 4.5 billion years ago, around the same time. And from what we understand, both planets actually formed oceans around the same time as well, around 4.1 billion years ago. And on Earth, at least, that was pretty shortly after that, the first life formed on Earth, and we have the first evidence of it. Small bacteria, archaea bacteria. But here's the big problem, is the next step to more complicated life, eukaryotic cells that are more familiar to you, single-celled organisms with a nucleus and specialized organelles inside them. That took over 2 billion years more. And this is the Earth with a fairly stable climate over that time. There was always liquid water on the surface, and it took 2 billion years to make that next jump. And the next jump from that, to go from single-celled organisms to more complex multicellular organisms, well, that took almost 2 billion years more. And then things start happening really quickly after that. Then you get the dinosaurs pretty much right away, and just on their heels, you get humans. So, and if you look at Mars, I've put a bar with some question marks at the bottom. That's pretty optimistic that Mars might have had a climate with oceans and lakes for around that time, 3 to 4 billion years ago. So that's one of the reasons we're really looking for really only simple forms of life on Mars. So why do we even do it? Why are we interested in finding life on Mars? What makes it important at all? Well, when it comes to finding our place in the universe and knowing how common life is in the universe, right now we have a sample size of 1. We have 1 planet that has the conditions for life, and we know that that planet has life. So if we find out that Mars had the right conditions for life, but that life never existed there, that actually tells us quite a bit about how common life might be in the universe. It might tell us that life is pretty rare. At least it tells us that we still only have 1 planet in the solar system and in the universe that we know has life. But if we find that Mars had the right conditions and life existed there, well, that's incredible. That means there's 2 planets in the same solar system that developed life. And then we can kind of start to make some assumptions about how common life might be in the universe. And we might guess that it's pretty common. So just leave you with the thought that the point of this is, whether or not we find life on Mars, either answer is hugely significant. And despite that, for people like me, for people like the geologists, just studying the geological history of a planet other than the Earth is hugely important to understanding the solar system as a whole. Thank you very much. Hi, man. Thanks. Yeah.
Така, сега ще направим една дискусия, която ще е свързана с презентацията на
Which is your
Зак.
good side? Yeah, thank you.
Слагам го тук, тъй като неговото лице за камерата очевидно. В смисъл, не е. Поне това ми обясниха от тех екипа малко по-рано. За тази дискусия обаче ще имаме нужда от вашата помощ. Отидете на slide.do. Там може да напишете кодче Марс и можете да задавате вашите въпроси, които ще се опитам да задам в следващия половин час. So, Zach.
Hello.
One of the first questions I wanted to ask is, you had one of your last slides was about the different epochs.
Yes.
Right? So, I mean, I didn't know up until your presentation that Mars had the same kind of epochs that we had, like Precambrian or whatever.
Yeah.
How did that, I mean, yeah, that's exactly.
Oh, yeah.
How did that come about? I mean, is it based on some geological evidence that we know that there's a pre-Noachian and Noachian epoch?
Yeah, it's really interesting. It's all based on what we know about the geology. So a lot of the epochs on Earth are actually based around what we know about the history of life. So it's no coincidence that multicellular organisms start up just before the Phanerozoic on Earth. That's kind of the definition of why that era started on Earth. Whereas Mars, we have to use different evidence. So it's what types of minerals were happening there, what was the surface conditions like. And for instance, the Noachian is defined by a presence of large bodies of water, potentially.
So it's based on Noah?
Yes, yeah. I mean, the original idea, yes.
You have to admit that somebody in America thought of that one.
Maybe, yeah.
Somebody in the Bible Belt.
It sounds biased, yeah.
So basically, when we look at the Amazonian, that's the period when we know that stuff really hit the fan, right?
Yeah.
So the Amazonian is the equivalent of everything is fucking dead now.
Yeah. I mean, once you hit the Amazonian, it's very, very cold, very dry from that point onward, as far as we know.
So that's essentially the effect of the shearing away of the atmosphere at that point.
I mean, that's one of the main things, is that once Mars couldn't hold its atmosphere anymore, eventually, if you don't have an atmosphere, the planet will just get very cold.
What are your thoughts on some of the ideas to terraform Mars? I mean, be it Elon Musk's ideas or less radical ones. I mean, what's your thoughts on potentially transforming Mars in a way in which it can actually hold an atmosphere? Or is that realistic at all?
At this stage, it's really science fiction still, unfortunately. The idea of changing the atmosphere of the entire planet. For our first missions there, I think we'll definitely have to live within habitats. You could build bigger and bigger habitats, but to change the entire climate of Mars, it would take so much material, so much extra gas to add to the atmosphere. And we just don't see that much gas on the planet to begin with.
So essentially, the only way to actually fix it is to bring more material in. There's no way to utilize, let's say, like the additional deposits, which are of carbon dioxide or whatever.
Well, it's interesting. It's a couple of years ago, a study was done trying to tally up exactly how much carbon dioxide and water there was. Even the most generous estimates, so adding up everything that we think might be in the poles and think might be under the surface of the regolith as well. And even then, even if you melted all of it, it would still only raise the atmospheric pressure a couple percent. And it's not nearly enough.
So for example, if we decide and go to Mars and not only blow a bunch of nukes, as Elon Musk suggested,
Elon, yeah.
Yeah, we also, let's say we introduce some kind of bacteria which would allow to generate some kind of additional dynamic there. Would that be something that would be workable, potentially?
Well, first of all, I think nobody let Elon get a hold of nukes. I think that's probably a bad idea. But even if we found a way that, say, bacteria could break down rocks or something to make the gases, it would be a very long, slow process. And it would be millions of years potentially, not just thousands of years.
And that ties in with the question of, is it ethical at all? I mean, if there's some chance of potentially finding some remnants of life on Mars, if you go and contaminate it either with ourselves
Yeah.
or with intentionally just go and try to terraform it with some biological agent.
Yeah.
Would that be a good idea? I mean, would us in general going to foreign planets and try to introduce some of our own bacteria, would that be ethically a good idea?
I mean, it's an interesting moral question, and maybe I'm not equipped to answer it fully as a humble geologist.
You're the rock guy.
Yeah, I'm just the rock guy. But I think a lot of it comes down to whether or not there's life there. I think if we search the planet for another decade and find that we're very sure that there's not life on the planet and there never was, then I don't think that moral question exists anymore. I think we can safely go there, and we can safely change it however we want.
Yeah, true, but I mean, you can never be 100% sure, right? So it's like you can only asymptotically get an idea of whether there's life there. Maybe there's something in the, I don't know, in the depths of past oceans or whatever.
Potentially.
So it's difficult to actually answer that question before bringing a bunch of shit.
Of course. And I mean, I think this is why we really have to stay focused on decontaminating things that go to Mars, and even if we send people, doing our very best to land in places that are low risk to contamination until we have some better idea of an answer.
So, for example, if we're looking at private missions, for example, not only SpaceX, but, I don't know, let's say somebody else, like Blue Origin, wants to land on Mars. What kind of incentive would they have to not contaminate Mars? I mean, would somebody sue them? I mean, what?
It's
fucking Mars.
It's a really good question. I mean, there's a lot of concern among scientists about, well, I mean, Elon Musk and SpaceX, they do a lot of things without asking anyone. So the worry is that, they could just send a mission, and who's going to stop them? It's space. There's no police out there.
Space police.
Yeah, exactly.
Trump will stop them.
Space Force.
Yeah, Space Force. Well, that's a common question that we usually get when we're looking for life outside of our planet is the approach that we're having to life in other places correct in general? I mean, is it reasonable to only look for carbon-based life, or to only look for life that has as a necessity water, or are we just putting like a boundary condition that just doesn't necessarily make sense?
Yeah, are we putting an Earth-centric sort of view on things?
Are we Earth-biased?
I mean, biology is not really my area, but I know there are some chemical and physical reasons that we think carbon-based life is probably more likely, but really it comes down to just knowing about life on the Earth. So it comes down to that thing of there's only one planet that we found with life, and as far as we know, what else are we going to look for? What other kind of signs could we look for even? So we're just basically starting with what we know.
Yeah, if we can't imagine what the effects of a differently based life would be, it would be difficult to look for them, basically.
Exactly. Hard to imagine.
And most of the time, you're not even looking for, the actual pictures of like an organism. You're looking for the biochemistry. So even on exoplanets, etc., you're looking for specific kind of, that's what you're looking for.
Oh, yeah. It's probably life, that one, yeah.
Yeah, so when you're talking about what kind of life we're looking for, how do we even define life? Would you say that it's somehow tied to, let's say, reproduction? Is a virus alive? Is a computer program alive? What's the definition? Does it have to be biological in order to say we find life?
That's beyond my specialty. I mean,
back to you, rock guy.
Yeah, but I mean, I think, as an example, I think if we found something like a virus on Mars, I think we would consider that evidence of life on Mars. Even though, we look at viruses on Earth and they're not maybe technically alive in every sense. I think you could consider that some form of life.
I think there was like a movie like probably like 15 or 20 years ago, that was we found the virus on Mars, and we brought it in, everything went to shit.
Oh, always. Yeah.
Yeah, I can't wait.
It's nothing good ever comes from Mars in Hollywood.
know.
It's very rude. I don't know why.
It's just fucking rocks, man.
Yeah.
Yeah, so there was a slide where you were explaining about the two rover missions in 2020. So one is the one by ESA and the other by NASA.
Yep.
So how do they actually prepare for those missions? I mean, do they, let's say, send them to like a deserted place on Earth? Or, I mean, how do you prepare for that kind of environment? Because it's really fucking specific.
Yeah, so I mean, it comes down to that concept of analog environments that I was talking about before. So the analog environments I'm looking for are environments that were there in the past. But to test a rover, we try to send it to analog environments that are like what Mars is today, as close as we can get. So cold deserts is the best. Actually, I took part in a rover trial just over the winter. So the ExoMars rover that's being built in the UK, it's the ESA mission, so it's all European instruments going on board. And that was they sent the test model of that out to the Atacama Desert in Chile.
Cool.
And then we controlled the mission from back in the UK.
You yourself control the mission?
Well, yeah, I mean, it's a whole team of people. So, but the interesting thing is, it's...
who was holding the controller?
But this is the cool thing, is there is no controller. I know, it's very disappointing. But
very cool.
Because on Mars is 8 light minutes away from us, so at the best. So we can't actually control anything in real time on Mars. So we tried to simulate it as best we could as a real Mars mission works. And that meant getting all of the information that the rover had taken on the previous day. We got about 12 hours to look at it, to make up some ideas about where to go next and what to do, typing in some commands, and then sending it all off in one batch to the rover. And then we had to wait until the next morning to see what had happened and where the rover had gotten to.
That's cool.
Yeah. So I think it was organized really well to try to replicate as close as possible what it would be like actually communicating with a rover. Oh yeah, that looks familiar.
That's cool. So if we have to get back to your specialty.
Yeah.
Water on Mars, right? So I'm guessing, judging by the your studies, you're mostly a proponent that there was an ocean on Mars, right? Because that's the controversy right now with water on Mars.
It definitely is a controversy. I mean, I'm more in favor that there was an ocean, but I understand the arguments against it as well. So even though we see signs in the geology that indicate that there was an ocean there, a lot of the people modeling the climate on Mars actually indicate that there was never enough water, or it was never warm enough, or warm enough for long enough for an ocean to exist. So it's really trying to balance those two. And where I'm landing on it is that I think there probably was an ocean there, but probably limited in its amount of time that it was actually a liquid. So it might have existed periodically and melted, and then frozen over, and was eventually buried potentially. But it's a really controversial area.
Is it possible that one of the questions from the audience is it possible that one of the ways that ocean formed is not with water, basically? Could it be some other kind of liquid that it formed? Yeah,
I mean, earlier on in Mars studies, there were more suggestions that even the valleys that we see on Mars were formed by some other liquid flowing across the surface. Most of that's kind of been discounted now. Having other liquids forming these oceans and lakes, it really just introduces more problems than it solves. And because we know there's quite a bit of ice on Mars today, water still seems like the most obvious choice for that.
I was actually going to ask you about this. You mentioned that there's like a top layer of not water, and then there's like a kilometer of ice water. So how do we know it's fucking ice water? I mean, we haven't dig up there. How do we extrapolate that?
So a lot of that's done by they can tell the density from some of the spacecraft, some of the radar. They can tell dense it is and what material it's made out of. But also we have spectral instruments on some of the orbiters. And that's using a particular wavelength of light to image the surface. And by that wavelength and what wavelengths actually return to the spacecraft, you can tell what material the surface is made of.
So, but that's specifically for the surface, though. I mean, when it's an optical kind of thing, it doesn't penetrate below the initial layer.
But there are cracks through the surface in some places.
Okay.
So there does appear to be melting every once in a while as well.
That's interesting. So one of the questions was, I've only heard of the theory of, Mars shearing away its atmosphere due to the activity of the sun because it lost its magnetic field because of a cooling off core.
Yeah.
Is it possible that the water on Mars disappeared because of something else, rather something related to more active core or some other kinds of internal heat that essentially boiled away the oceans or something similar?
I've not heard any theories like that. The fact that the atmosphere was probably stripped away by solar radiation that's the leading theory at the moment. But some theories don't really account for how much volume has been lost. So that's why I mentioned the oceans possibly being buried under regolith or rock as well. So that's another indication. That might be where some of the water went.
That's cool. Buried oceans.
Yeah.
So by buried, you mean that they're essentially some form of pockets of water that are underneath, or rather they're essentially soaked into the ground?
Yeah, more like the latter, or we're possibly just it's layers of ice and water underneath the surface. Rovers, other landers have actually dug just a little bit under the surface in some other parts of the planet, and they do see water ice directly under the surface when they dig, but that doesn't necessarily mean that there's huge amounts of it. It could just be near the surface. But yeah, closer to the idea that it's that water may have soaked in and remained there.
I think probably in the last week, there was news reports of some kinds of seismic activity on Mars. I'm not sure if you managed to check that out.
Yeah.
So what would that be? Because if we assume that the core has been dead for a while and there's no plate tectonics, so I mean, what would the active bit of Mars be? Would it be some kind of I don't know, something related to gravity?
So the mission that made these findings is the InSight lander, which is it's a lander. It landed just in those flat plains that I showed you on Mars, and its main mission, it was to place a seismometer directly on the surface. And basically what it's looking for is, Mars quakes, this seismic activity. But the main reason that we think these Mars quakes actually happen is asteroid impacts, meteorite impacts onto the surface. So it's possible that it might detect some other form of tectonic activity, but almost certainly what it's picking up are meteorites impacting into the surface.
So, for example, it's not something like the tidal effects that we get on Earth from the moon with Phobos and Deimos?
No, Phobos and Deimos are very, very small. I mean, they look more like captured asteroids around Mars. They don't really have very much of a tidal force on Mars at all. But there are other strains on the crust of Mars. So the biggest valley on Mars, the Valley Marineris, I forget the superlatives used to describe it, but it's X times bigger than the Grand Canyon and much, much deeper and things like that. But that would have actually involved some faulting to open it up, to open this big crack on the surface. But yeah, not by plate tectonics, but because the weight of a huge amount of volcanoes on one part of the crust actually warping it and settling it down and just cracking the crust around it.
That's cool.
Yeah, very cool.
So when was the last time that we can say that Mars was potentially geologically active? I mean, is it somewhere in the pre-Noachian?
I mean, to define what you mean by geologically active is maybe a bit tricky, but from what we can see, I mean, up until I think around 100 million years ago, the largest volcano on Mars was actually active. So that's Olympus Mons. It's actually the biggest volcano in the solar system and the biggest mountain as well. It's absolutely massive. But that was actually active around 100 million years ago. So that's within the Amazonian. That's actually fairly recent in terms of the age of the planet.
If we have to go back to the questions for the oceans, etc., given the instruments that we have now and potentially the missions that we are planning, would we have a better idea of what kind of compositions those lakes or oceans used to have? I mean, is there something that's addressing specifically that rather than a composition of soil, etc.?
What composition the waters might have been?
Yeah.
Yeah, it's a really interesting question, and it's one of the problems that we see. There's things that we would expect to see if there were oceans and lakes, oceans particularly on Mars, that we don't see. For example, we don't see any carbonate rocks on Mars. This is like limestones on Earth that are formed by taking carbon dioxide out of the water and out of the atmosphere and forming into rocks. Now on Earth, a lot of the time that's helped by life. But even without life, we would expect some carbonates to form if there were oceans there. And because we don't see that, it either suggests to us that there was something different about the chemistry of that water. Maybe it was if it was really acidic or very salty, very saline, that might mean that you would not get carbonates forming. So that's one of the ways that we can guess what the composition of these waters might have been. But generally, the thinking is they were probably much more acidic than oceans on Earth.
And one of the questions that was mostly covered in your talk, the whole body of your talk, essentially, but I think it's worth discussing a bit more, because if you ask a random amount of people on the street, I mean, I'm guessing you're going to get an answer of, yeah, I think there's been life on Mars.
Yeah.
In some shape or form.
Sure.
So, I mean, and there's a few things coming out of this. Do you suppose that if there was life on Mars, potentially, at some point, it could have seeded life on the Earth? Do you think, given the timelines that we saw? And would you suppose that, even given those short time frames, that kind of life was similar to Earth's? If we have to speculate, obviously, it's a wildly speculative question.
Sure. So yeah, the theory is called panspermia, right? The idea that life could travel from one planet to the other and seed life there. So, I mean, whether it's possible for life to survive that journey or in any way could be tricky, but we do know that rocks have actually survived being blasted off the surface of Mars. So when there's a big impact onto the surface of Mars, sometimes it would be able to fling rocks out into orbit that eventually hit the Earth. And we have examples of that. We have meteorites on Earth that we know are actually rocks that used to be on the surface of Mars. So we know that you could transfer material like that, but how likely it is that that happened with life, that's a whole other question.
Yeah, because something needed to hit Mars in order to shear something away.
Yeah.
Yeah.
And that happens. We know that happens. It's just whether or not life could actually survive that journey.
Yeah, my money is on life.
Sure, yeah. Life finds a way, as
finds a way.
Wise man once said.
When you mentioned the Mariner Valley,
yeah.
I mean, we have some pretty fucking cool names of places on Mars. Is there like a naming convention for this? Is there some scheme under which we name stuff on Mars?
Yeah, so there's an international astronomical union that decides what can be named and then what names are actually given. And in the early days of Mars, like when Schiaparelli was looking at things, it was kind of a free-for-all. I mean, if you discovered something and wrote a paper on it, you just name that, and everyone would start using that as the common name for that particular crater or feature. But now it's quite specific about how you name things on the surface. So if you want to name a valley on the surface of Mars, it has to be named after a river here on Earth. And if you want to name, most of the big craters already have names, but if you want to name one of the smaller craters, it actually has to be named after a village or town on Earth, I think it has to be a population under 10,000. So there's very specific rules about what you can use for names. I don't get to decide these things.
Okay, here's my pitch. Here's my pitch.
Yes.
I name a town after me.
Yes.
I get 10,000 people there. Then I apply.
That is a long game sort of goal, but I salute you. Yeah. Also, generally, you can only name something if you have a good reason to. So you have to be writing a paper about that area on Mars generally, and then you can say, I need this crater to have a name, so I can call it by its name rather than just saying crater B.
Okay, extended.
So
pitch.
I'll help you with that.
Exactly.
Yes, yeah. I'll write the paper. You start your village. And then we're good.
I can't wait to start my village. I feel like a villager already. Okay, so do you suppose that actually underwater, water below the surface of Mars could be liquid? I mean, and given the temperatures there, how would that happen? I mean, given that Mars is not geologically active, there's no heat coming out from below. How would that work?
Well, it's not that there's no heat coming from the center of the planet. It's just not enough to keep an electric field active like we have on Earth. So there is definitely heat coming from the center of the planet.
It's still cooling down then?
Sorry?
So it's still cooling down?
It's still cooling down. It takes a very, very long time for a planet to cool down. It's just Mars has cooled down beyond the point where it has a core that was active like the Earth's, forming a magnetic field. So there definitely is warmth below, and that's one of the things that would actually create these lakes that they think they found underneath the ice sheets. So if you go far enough down, eventually you get a balance between the cold from the surface and the heat coming up from the planet that might be just right for liquid water.
So would you say that, for example, with one of the rovers that can dig up to 2 meters, would they be able to see some amount of residue or some traces of liquid water, or is that too shallow?
I think that's too shallow. Yeah. Mostly what they're looking for is
you have to go deeper.
We have to go much deeper. You have to send a much bigger drill. But yeah, that's for missions in the future.
Yeah. Cool. I saw that he has a Twitter. Spoilers.
I do. I'm so hip like that. I'm very cool. The Twitter.
Yeah, hip.
Yeah. Mm-hmm.
I saw that you post some amount of caricatures and stuff.
Yes.
And obviously, you being a rock nerd,
yes.
I saw some stuff that's related to like minerals or something along those lines. So, is the fact that you're doing some kind of art helping you in your work and vice versa? I mean, would you say that you as a scientist, as a geologist, allows you to make better art in general?
That's really interesting. I mean, I think the art definitely helps me in my science, for sure, because it gives me, I can make my own figures, I can actually describe things in a visual way that people will understand. It's great for reaching out to the public as well, because people are more likely to look at a nice image than read a couple hundred words of text. So I think that way it really helps. But yeah, and I think it must work the other way around as well. I think it's, if only for my relaxation. It's
and
definitely,
your sanity,
yeah. It's definitely nice to have something else to focus my brain on other than Mars.
For example, with drawing, especially you as a geologist, is this like a skill that's kind of required for you to do? Because, I mean, you do a bunch of mapping, actual, I don't know what even the term is, but like, you make maps.
Yes.
Right?
Yeah.
So would that be like a core skill of a geologist?
Yeah, it is. I mean, it's still, when you do an undergrad in geology, it's still one of the taught things that you learn to draw maps by hand, and you even learn to draw sketches of the rocks that you see in the field and their layers. Because by drawing them, it really helps focus your mind and focus on what the rocks look like and what's happening there. In more detail than you would actually get with a picture. So it's definitely, I mean, people, it might seem a bit old-fashioned, but in geology we still do a lot of drawing and coloring.
I don't know, it does look like old school cartography.
Yeah.
Somewhat.
It kind of is. I mean, it's essentially, there's so much data on Mars, all of these pictures that have been taken of the surface, and just not enough scientists to actually look at it. It's really incredible.
Okay. So, knowing that, would you say that basically your professional skills in, recognizing specific patterns on the surface, potentially, posing some questions and then checking those questions, having like a theory about something, etc. Would you say that this is long-term potentially doable by AI?
Yeah, it's a really good question. I don't know for sure. I mean, I feel like there's so many variables in the interpretations we're making that I don't think you could do it all with artificial intelligence. Some people, they're trying some programs to map the surface of Mars by teaching neural networks, but it's early days. I mean, I think there's potential there, but whether or not it could completely replace geologists, I hope not. But
that's what you say.
Yeah.
So if we have to move back in speculative territory again, what would you imagine would happen if we, end of the day, managed to have like a permanent settlement on Mars, and like a regular settlement, something that would allow for production or for some kind of industry in general? Would you say that this would somehow create an imbalance in terms of economies, in terms of the balance of power politically, etc.? I mean, you've probably read like a bunch of sci-fi novels, like The Expanse, etc. It's fucking crazy.
Yeah.
I mean, would you say that this would be like an upset? Would it be like new gold rush, for example?
Yeah, potentially. It really depends how efficient we could be at living on Mars, because I think almost certainly for a first long time, if we were to set up a settlement on Mars, everything for that settlement would have to come from Earth. It'd be a long time before it was actually self-sustaining. So, I don't know. I mean, I think eventually, yeah, it would, after a couple generations of people living there, they probably wouldn't identify themselves in the same way as we do on Earth. They would think of themselves as Martians, potentially.
True.
So, already from there, you've got a very political difference.
Yeah, when with generations, they're probably going to change a bit.
Yeah.
Geologists go deeper.
Oh.
Wow.
Yes, yeah.
On that note, one of the questions is amazing. It's, what did it go? Fuck. It was, is it possible that the life on Mars had a hangover and drank all the water? Wow.
Very possible, yeah.
I think that's, I mean, end of the day, I don't know, I'm kind of skeptical, because obviously the only way to cure a hangover is with more alcohol. So just never,
But we don't see any alcohol on Mars either, so they must have drank that, all of it, and then they were only left with the water.
Those guys are hardcore. So if we have to go back to the geologist bit, what made, beyond going deeper, what made you choose your specialty?
Beyond that, obviously, yeah.
Way beyond that.
Yeah. I think the thing that really fascinates me about geology, it's not the rocks actually. The rocks are just what we look at. They're kind of our tools. But I love geology and the fact that it deals with such huge amounts of time. I mean, the way just in this evening I throw around terms like billions of years so easily, it really diminishes it, I think. I mean, it's quite awe-inspiring when you think about just the amount of time involved in forming these things and forming the planet as we see it today.
Would you, I mean, given that your specialty right now is specifically Mars, if the opportunity arises, Would you want to try and apply the same skills to an exoplanet? Let's say, let's imagine we have the same amount of data for a planet outside of solar system. Would you be interested in working on that shit?
Oh yeah, absolutely. I mean, it's...
You have no loyalty.
No. I'm not a Martian. I don't have no patriotism.
Yeah, you don't have like a double passport.
No. No, the idea of seeing a new planet and looking in detail at its surface would be incredible.
So when we said that there's no regulatory framework for having bacteria, etc., be introduced to Mars, is there some other kind of multinational treaties that regulate at least, owning land on Mars, or that's...
Yeah, I forget exactly how it works, but I think the international treaties are basically, they're voluntary anyways, so you don't have to sign up to them in general. Even the really important ones, like the demilitarization of space, like it was decided during the Cold War that nobody was going to put nuclear weapons in space, because everyone agreed that that was a terrible idea. So, but
that's a cool idea.
Yeah. But I know on the moon, I believe, countries can't actually own parts of the moon. But the thing is, when it comes down to it, the only way that I could really think of to police, private organizations is to limit where they launch from. So, say SpaceX went to Mars and started doing something we didn't like. Well, the American government say, well, you can't launch anything else from our soil anymore, which that's about the only thing that they could do.
Soft instruments, basically.
Yeah, but no, I mean space. It may sound silly, but space law is actually a new academic area. People are actually trying to write up these treaties that we might have to use not too far in the future.
Sounds like a really good movie series, like a space law.
Space law. Bum, bum.
I own a fucking thing on Mars, it's mine. Oh no.
It's just like Judge Judy space law.
Exactly, that's the same. Space lawyer. Oh,
there you
shit.
go. Yeah.
They even got to Mars first.
Yeah.
We got like a bunch of rovers and this guy on Mars. Jesus. One of the amazing questions is also related to some of the pictures that you showed for Mars. And it looks kind of round, so it's not flat like Earth.
Yes.
Is this true?
Yeah, it's very odd, isn't it? All of the other planets we look at and all the moons are round, but I don't know how the Earth ended up that way, but it's a very good question. There's probably a PhD research in there, actually, if someone wants to start it.
Yeah. Okay, so the last question is from Vladi, who is 5 years old. Are the Vulcans on Mars?
Vulcans?
I'm guessing for Star Trek?
Like Mr. Spock, and yeah. Well, I've not seen them.
Don't fuck it up. Don't fuck it up.
But who's to say? I've not seen them myself yet, but I'm going to start looking harder now.
Cool. Well, Zach, thanks a bunch for the interesting discussion, and thanks a bunch for the talk.
Yeah.
Hope you had a good time.
It's been fantastic. Thanks for having me. Cool.
So, geologists go deeper. Tell your friends. Благодаря ви всички, че присъствахте днес на първото ни събитие от поредицата с Европейската космическа агенция. Надявам се това, което чухте днес, да ви беше интересно. Не забравяйте, че имаме още серия други събития до края на месеца, които отново са на космическа тематика. Две от следващите, които ние организираме, са Ratio представя космически двигатели. То ще бъде заедно с Стоил, който ни беше лектор на едно от събитията, които правихме в музейко. Той е доста интересен гай. И съответно нямам търпение да видя точно начин, по който ще представи тъмната история на всички начини, по който мога пътуваме с двигатели в космоса. Той е и инженер, и архитект, така че съм сигурен, че има нещо много интересно да каже. Следващото ни събитие е космически балет И изключая визията, която ни е повече в посока на събитие за откриване на чакри и някакви такива неща, всъщност ще си говорим отново за наука. То ще бъде с лектора, който ползвахме за звезди при няколко седмици. Това, което там ще засегнем е точно какво представлява въртението като цяло, като концепция. Какво информира нас за формиране на слънчеви системи, какво информира за движението като цяло и прочее. Евентуално ще говорим и за гравитационни асисти и сходни неща. И не на последно място, Ratio 2019 есен. Подготвили сме ви доста яки неща. Отново само ще подчертая, че следващата ни тематична лекция, която е с Европейската космическа агенция, е там. Робин Андрюс се казва лекторът ни, той е вулканолог. Той е отново kind of a rock guy. Не е геолог, което е лошо за него, предполагам. Той ще говори за вулкани и серия странни катаклизмични ивенти, които се случват в нашата Слънчева система. Както той казва, The Solar System is a freak show. Така че Робин е доста интересен. Той пише между другото за I fucking love science, за Forbes и някакви серии други неща. Така че може би компенсира се малко, нали, там, геолог спрямо това. Има също серия други интересни неща, които се случват тогава, но вижте в страницата. Не на последно място, имаме също и подкаст, който в момента, в който не съм безбожно болен и ужасно скучен, като днеска, извинявам се, понякога сме интересни. Имаме и записан подкаст вече с Зак, като практически 90% от въпросите, които минахме по време на подкаста, не сме задавали сега, изключително много се гордея със себе си. В интерес на истината, не знам дали това беше добра идея, но да. И ако искате да ни подкрепите под някаква форма, тези събития са безплатни, опитаме да се правим 3 до 4 събития на месец, опитаме се да правим и подкаст и някакви други неща, и видеа, и прочее, и тук хора мъкнат техника, в смисъл, случват се неща, нали, Patreon /RatioBG, ей, двамата човека, които дават пари, се обадиха, които са от нашия екип. Seriously, в смисъл, подкрепете ни, от време на време пием бира, това е начинът, по който ние придобиваме. Благодаря ви отново, че дойдохте днес. Лека вечер!